Okay, so today we're doing 3D.1. We're going to continue learning about our functions and shape. So what we've seen is if we have a function, all right, we put an x value in, it tells us the y value. If we have the derivative function, it tells us the slope, right? And so the sign diagram of the derivative function tells us when we have a positive and negative slope, when it's increasing and decreasing. And so that tells us when the stationary points, like our local max and local min, occur. If it's increasing and then decreasing, we have a local max, right? What f dash dash of x tells us is about the shape. So we're going to be drawing sign diagrams of the second derivative as well today. Because the second derivative reveals to us where points of inflection occur. So a point of inflection occurs when the second derivative is equal to 0. If the second derivative is positive, all right, so if the sign diagram is positive, the function is concave up. And if the second derivative is negative, the function is concave down. Let's talk about what both of those mean. So here, this point here is what we call a point of inflection. That's because it's where the graph changes shape. Notice how over this region, the function is opening downwards. We call that concave down. It's opening downwards. And here's the point of inflection where it inflects, it changes its shape, and it goes from concave down to concave up. So that point of inflection there, that's going to occur when the first derivative equals 0, and the second derivative equals 0, and the sign diagram of the second derivative changes shape. Now, that is listed in the second paragraph at the top of our page. First paragraph, sorry. A point of inflection occurs when f dash dash of x equals 0 and the sign diagram changes sign. Visually, it's a description of when the slope changes from increasing to decreasing or vice versa. So at this point, all right, what's going on is the slope is decreasing and then the slope starts to increase, which means the slope starts to get larger. That's one way you can understand it. The point of inflection occurs when the function changes shape. That's from concave up to concave down. Below the point of inflection occurs at A. All right, so the function here is concave up over that region, which means over this region, so for values greater than A, the function is concave up, which means the second derivative is positive. And over this region, the function is concave down, which means the second derivative is negative. Let's get into the example that we're presented with. Oh, still carrying it. So we've got x to the 4. Take 4x to the 3 plus 5. Okay, so let's start with the graph and let's see if we can see where the points of inflection occur. I might even sketch as well so that I can point to them. So it's got this shape, right? Here's our Cartesian plane. It's going like this and then like this. Okay, that's the shape of the graph. Now we can very clearly see that it's concave up over this interval, which means it's changing shape somewhere here. We'll find the exact point in a moment, but we have concave up. There's some point of inflection here where it changes to concave down. And here we have what we learned about yesterday, a stationary point of inflection. All right, so that's the special case. It's a stationary point of inflection because the slope is horizontal. It's not increasing or decreasing. And it changes shape. Over that region, okay, concave down. Over that region, concave up. So it's changing shape and the slope is horizontal. We have a stationary point of inflection. And here, it's non-stationary point of inflection. So that's what we call it, a non-stationary point of inflection. Okay, so we can observe those features from looking at it. We're going to find them algebraically now. So let's differentiate the function. All right, that's our derivative function. We can use that to tell us about the turning points. So the derivative function can reveal to us the coordinates of that point, the stationary point of inflection, and the local minimum. So maybe we'll recap that quickly. Like if we draw the sign diagram of this one, we would factorize it. X take 2, take 3. All right, and if we apply the null factor law, we have x is 0 or x is 3. And so that's going to give us this sign diagram for the first derivative. All right, so we have a root at 0 and a root at 3. It's a cubic equation, so it's going to go like this because it has a positive a value, which means it's below, above. And what that means here, decreasing slope until we get to there, then decreasing again until we get to here at x is 3, and then increasing, right? This sign diagram mirrors what we see on the original function, okay? Decreasing, negative slope until we get to 0, then we're decreasing again until we get to 3, and then we're increasing, okay? So that's the sign diagram there. Now this is what we did last lesson, right? This reveals to us we have a local minimum at x is 3. We can see that, of course that's the case. It's decreasing and increasing. So we have a local min at x is 3, and then the corresponding y value. And we have what's going on here. This is what we learned about yesterday. When the first derivative has that feature, negative, negative, or positive, positive, it's a stationary point of inflection. So we have our stationary point of inflection occurring at x is 0. When x is 0, the y value is positive 5. Okay. So that's our first point of inflection, but let's look at how we can use what we've learned today. I said we need to find the second derivative. So what that means is I'm going to differentiate this function here. We would get 12x squared take away 24x. All right, so we've moved from a quartic. When you differentiate a quartic, you get a cubic. When you differentiate a cubic, you get a quadratic. And well, let's draw the sign diagram of this quadratic. If we want to find its roots, we make it equal to 0. We'll factorize 12x. And we get x is 0 or x is 2. So they're the roots of the sign diagram for the second derivative. And this is a quadratic. It has a positive a value, which means it's opening upwards. It's our happy face. So positive, negative, positive. So that's the sign diagram of the second derivative. Now, what we've learned today, let's have a read of the dot points here. The very first one at the top under 3D.1. A point of inflection occurs when the second derivative equals 0 and the sign diagram changes sign. So just based off of this, that's a 0. I mean, it's a 0 in two senses. It's a 0 and it's a root of the second derivative, right? It's where the second derivative equals 0. And notice the sign diagram changes sign. So we have a point of inflection at 0. All right, so we have a point of inflection at 0. And we have another point of inflection here. This is a root of the second derivative. It's where the second derivative equals 0. And the sign diagram changes sign. So both of these are points of inflection. Now we've already found one of them, right? One of them was revealed to us in the first stage. It was revealed to us when we did the first derivative sign diagram. The first derivative sign diagram will reveal stationary points, and a stationary point of inflection is a stationary point. So it's found there. But we've found the other stationary point, this one here, the other point of inflection, sorry, this one here, which is a non-stationary point of inflection, occurs when x is 2. All right, so we'll write that down. Non-stationary point of inflection at x is 2. All right, now when I'm doing a question like this, I'll always do it like this, right? I'm going to set out, yep, we need that piece of information, that one, and then this is a great way to be efficient with your time. Just G-solve all of them right at the end, okay? Rather than typing it into the original function. It takes a long time. You've got to be optimal. Talk about optimization. You've got to be optimal with the time you're allocated. And so leave them blank, and then right at the end, do a G-solve, fill all of the answers in that we need. So we know there's points of inflection here and here. We found that one, that was easy, but we got when x is 2 there. Good, okay, so that's the first part. Now we are asked, state the nature and coordinates of any points of inflection. Okay, so we've got the coordinates, and this is the nature. We have two types of points of inflection. They're either stationary or non-stationary. So fantastic, we've stated their coordinates and nature. Hence, state intervals where the function is concave up and concave down. Well, that's in the underneath our diagram here. It's highlighted for you. F of x is concave up when the second derivative sign diagram is positive. So we're going to look here at the second derivative sign diagram, and we're going to say the original function, f of x, so I'll just write it like this, sorry, complicated. Concave up when x is less than 0 and x is greater than 2. Okay, that's when the second derivative is positive, and concave down the opposite when it's negative, which is between 0 and 2. All right, and we can see that from the graph that we've got anyway. Look at the graph. All right, observe those features that we've demonstrated with the calculus techniques. Concave up for values of x less than 0. Concave down between 0 and 2. Concave up for values of x larger than 2. Okay, so observing that shape, observing those features. Really good. So that's question 1. Now, the only way to determine the nature, there's multiple ways I suppose, but I said we need to decide the nature of the points of inflection. Now we should be able to recognize it by looking at it, okay? By seeing it's stationary there and it changes shape, so that's a stationary point of inflection. You can see that from looking at the graph. Here, it changes shape, all right? It's concave down over that interval, concave up here. Changes shape, but it's not stationary, so non-stationary. So we can observe that by looking at it. The other way is that stationary points of inflection always occur on the first derivative, the sign diagram of the first derivative. So always check the first derivative. Notice how the stationary point of inflection, not only does it occur here, but it occurs on this one as well. It will occur on both. If it's stationary, if it's non-stationary, it will only occur on the second derivative. Must have the sign change. Good. What we'll do, we're going to stop there because question 2 is a long one, and this is a fat exercise, by the way. You thought the tangents one was a big one. Shooting for the sky. So the y value is approaching positive infinity. Now, let's justify that mathematically. What we would do is put a really big number into this equation. So if I put 1,000 in here, I would have 1,000 squared, 1,000 times 1,000. And then we're multiplying that by e to the power of 1,000. And e to the power of 1,000, what does that mean? It means 2.72 times 2.72, 1,000 times. So we just have this enormous number, all right? So we can just see the larger the number gets, the larger x gets, the larger y gets. Y is getting enormous. As x approaches infinity, y is approaching infinity. Okay, we're going to see something different as x approaches negative infinity. So as we move to the left of the graph, if we keep moving along, you can see this in your calculator, it's getting closer and closer and closer to 0, 0.04, 0.03, 0.02, 0.01. However, it will never reach 0 because it's asymptotic. Let's demonstrate why. So again, what we're going to do now is put a really big negative number in. So I'm going to put minus 1,000 into this question. So we have minus 1,000 squared, and we have e to the power of minus 1,000. This will be a positive number, all right? But this one is going to be much larger, and this one is 1 divided by 2.72 times 2.72. So because it's a negative power, we can take it to the bottom. And that times 1,000 is an enormous number. But I think the point of it is to say, yep, this part's going to be positive, this number's going to be positive. Here we have 1,000 times. And so what we have is we have a big positive number multiplied by 0. In fact, the larger our number gets that we're substituting in, the closer and closer and closer it's getting to 0. But it's approaching 0 from the positive direction. Okay? From the positive direction, meaning this number is still a positive number, although it's very, very close to 0. Okay? It's approaching 0 from the positive direction. Another example I had a student just asking me about before was this one. Okay, this is the graph of 1 divided by x. What we can see is as x approaches positive infinity, y approaches 0 from the positive direction. All right? And as x approaches negative infinity, y approaches 0, but from the negative direction, from below the x-axis. Okay, so that's what that kind of language means. So that's the answer for part A. We can observe it in our graph and we can think about it mathematically. Encourage you to do both. Okay, let's do part B. Find f dash of x and draw its sign diagram. So in order to differentiate this, we're going to need to use the product rule. U dash, v dash. Smash them together. Plus. Okay, for us to draw its sign diagram, we need to find the roots. We need to find when it equals 0. So we would factorize x e to the x. And then we could apply the null factor law. X equals 0, e to the x does not equal 0, x equals minus 2. So we have 2 roots on our sign diagram. Now, how can we use our calculator to help us? Well, we can sketch the function, and we can sketch the derivative function, and look at the roots on the derivative function. X is minus 2, we see that one, and x is 0, we see that one. Those are the 2 roots of the derivative function. So we'll draw the sign diagram on it, minus 2 and 0. And what we can see is it's above, it's below, and then it's above. So that's our answer to part B. Okay. Part C. Hence. All right. Always keep an eye out for hence. Anywhere it says hence, it means using what you just did. Using what you just did. State intervals where the function is increasing and decreasing. Well, remember, this is the sign diagram of the first derivative. It tells us the slope. It says we have positive slope for values less than minus 2. What that means is we're increasing for x is less than minus 2 and x is greater than 0. Those are the regions we have positive slope. We're decreasing from minus 2 to 0. This is a recap of exercise 3B. Now in 3D.1, basically from question 4 onwards, you will recap 3B, 3C, and the skills we've learned in 3D. All of them are combined into one exercise, just like this question. So here's 3B, increasing, decreasing. All right, on to part D. Hence, state coordinates of any stationary points. Well, we can see from this sign diagram, from the sign diagram of the first derivative, that the original function is increasing and then decreasing. Positive slope and then negative slope. We have a local max at x is minus 2 and a local min at x is 0. Now you are always putting the x value into the original function. Always the original function, because we're using the derivative and the second derivative to make statements, talk about the features of the original graph. So when we put x is 0 in, we'll have y is 0, and when we put x is minus 2 in, we would have 4 on top of e squared. Okay, so minus 2 squared is positive 4, e to the minus 2, we can take it to the bottom. So we've got local max, local min. All right, part E. Find f dash dash of x and draw its sign diagram. So the second derivative. So that means we need to differentiate this function. This is our first derivative. We need to differentiate this function. Now I'm going to do a little shortcut because we already differentiated this. We did it here. That's the original function. And so we know if you differentiate this whole thing is what you obtain. So we know that part goes to here. So that means we just need to differentiate that part and combine them together. So we're going to have u is 2x, u dash is 2, v is e to the x, v dash is e to the x. Alright, so here's the second derivative, d squared y on dx squared. So the first part, I'm just focusing on that first part, u dash v plus uv dash. Alright, so that's the derivative of the first part. And then we know that when we differentiate the second part, that it goes to that whole thing again, which is 2x e to the x plus x squared e to the x. Alright, so that's going to be the second derivative. Now let's simplify that one. So that's going to be, these are like terms, we can add them together. That's 4x e to the x. And we'll factorise e to the x. Now we could find these roots exactly for the sign diagram using quadratic formula if we wanted to. Alright, so we can quadratic formula or put it in our calculator. E to the x will never equal 0, so those are going to be the points of inflection. But let's just refer to our graph for the sake of time. So here's going to be the sign diagram of the second derivative. Again, on your calculator, we're aware there's a feature for the second derivative. I'm going to graph the second derivative. The roots, it tells me they're irrational, minus 3.414 and minus 0.5857.
Something went wrong. Please try again.
Hey Siri. Minus 3.41 and minus 0.586. And what we can see is it's above, it's below, it's above. So that's the second derivative. Alright, we'll just break the parts up. Find f dash dash of x and draw its sign diagram. Done. Okay. Now we're going to use this to talk about its shape and its points of inflection. I'm going to leave that part there, I think, hopefully. So we're up to part F. Hence find the nature and coordinates of any points of inflection. Well, we have two non-stationary points of inflection at minus 3.41 and minus 0.586. So non-stationary point of inflection at and all right. So we'll find the y value in a moment. Now I know they're non-stationary. Sorry, I know they're points of inflection because they appear on the second derivative and the sign changes. I know they're non-stationary because they don't appear on the sign diagram of the first derivative. Remember, if they're stationary, that means they're a stationary point. These coordinates, those roots, do not appear on this sign diagram, so they have to be non-stationary. Alright, so find the nature and coordinates. So the nature, non-stationary, the coordinates there. State intervals where it's concave up and concave down. So to answer our last part, it's concave up when it's positive. Alright, so the original function is concave up for x is less than or equal to minus 3.41 and greater than or equal to negative 0.586, and then concave down in between that region. Okay, let's observe that feature on the original graph. So I'm really going to exaggerate it. All of these things we can see on the original function. Let's have a look. So I'm going to turn off the derivative, go back to the original, and I'm just going to change my y a bit. I'm pretty happy with my x values, but let's just change y to just be something like from -1 to 1, so we can exaggerate the features. Okay, now we're told the first feature is we have a point of inflection at x is minus 3.41. Look at that. Okay, so what I'm going to show you is it's concave up, the shape is opening upwards, and at this point it changes to concave down. That's a bowl, it's opening downwards. We have that downward shape there and the upward shape there. So we can get the y value that we need. So make sure you go back and fill them in, 0.384. And the other one we have is that x is minus 0.586. Okay, so the other point of inflection here, look, concave down in between those regions, and then concave up. Fantastic, okay? So we can see the points of inflection, and we can see the change in shape. All right, we also have a local max at x is minus 2, that's very clear. Local min at x is 0, that's very clear, they're the stationary points. And, okay, the last feature that we see in 3b, the original function is increasing. Look, as I walk along, it's increasing until we get to that local max. Then we're decreasing until we get to 0, and then it's increasing again. All of those features we found using those calculus techniques. Now I said this will pop up, most commonly in 3D.1 question 4. If you have a look at it, you see it says, find the turning points, find them increasing and decreasing, find the points of inflection. It says find all of those features that we've already explored. All right, we'll stop there. So 3D.1, that's enough for you guys to